AC, an abbreviation standing for alternating current. This is the form in which we receive electricity to our houses. From the power point, it can then be converted to DC, direct current, where required for devices such as laptops. But how do we represent alternating current? It clearly isn't as straightforward as for direct current. The sine wave, one of the big three trig functions, the key to representing alternating current and applying it in calculations. Let's look at a sine wave that represents AC voltage. The peak voltage is found from the amplitude of the graph, and peak-to-peak voltage is double the amplitude, or the difference between the peak and trough. Period is going to be the time taken for one complete cycle of the wave, where it starts to repeat itself, and if you need to find frequency, it can be calculated by 1 on the period. For current, the wave is going to look very much similar, but current will be plotted on the y-axis instead of voltage. Let's look at how we represent these waves mathematically. In this representation of the sine wave, there are a few components to look at. Firstly, the multiplier on the front is the amplitude of the graph. In the case of a voltage representation, this is the peak voltage, and peak to peak could be acquired by doubling this value. In the current case, it is clearly the same, giving the peak or maximum current value. Next part to look at is the lowercase omega, which is the coefficient to t, the time. Omega is the angular velocity, which is angular distance divided by time, where angular distance is in degrees or radians. For our uses, this is equal to 2 pi on the period, or 2 pi times the frequency. The final component of this mathematical representation is the plus or minus theta. This is the phase shift. A positive theta value shifts the wave to the left however many degrees, and a negative value shifts the wave to the right. There is also a phase relationship between waves. If V1 is shifted further to the left than V2, then V1 is said to lead V2, and V2 is said to lag V1. Looking at an example voltage sine function, in this case the amplitude Vp is 5, the angular velocity is 20, which can be used to find the frequency or period of the wave, and the wave is shifted 30 degrees to the left. Adding a second function, we can find the phase relationship between the two. Finding the difference between the two, it can be seen that I is shifted 10 degrees further to the left than V, therefore the phase relationship between the two is I leads V by 10 degrees. All these values can be measured experimentally in the lab using an oscilloscope.